Well, welcome to question 6 from the end of chapter 14 in the book Fundamentals of Particle Technology. This is the second part of the answer to question 6. The first part of the answer considered the theory that we're actually going to use here. So this is the nitty-gritty calculations, whereas the first part was the nice easy bit which just discussed the theory. A lot of text here, and we're going to have to use Excel in a moment or two. I'm not going to read out all the text. Basically, it's a small cyclone which we have laboratory test data for, and this is an 8-inch cyclone. If I can just get the pen to work. Okay, so this is an 8-inch cyclone, and we're going to use test data from this 8-inch cyclone in order to model the performance of what is called a 5 feet diameter cyclone, 12 inches in a foot, so 5 12s are 60. So to maintain the same units, we're going from an 8-inch cyclone to a 60-inch internal diameter cyclone. And the basis of our ability to be able to predict the performance of the larger cyclone is due to this concept of the grade efficiency being a unique value of the Stokes number. The collection efficiency at a particular Stokes number will be the same in both of these cyclones. So we're going to work out or transform is the technical term for it. We're going to transform the efficiency data that we are given in the table just here. Okay, this collection efficiency in this table just here, we're going to transform it from the sizes that are given in this row into what the equivalent sizes will be in our larger diameter cyclone, our 60-inch cyclone. So if we call this system A, if we call the model one system A, we're going to call the commercial one, the industrial one, system B. So in other words, we've got this collection data at system A sizes. We're going to convert that to system B. Okay, but in order to do that, we're going to have to change these particle diameters. Instead of 1, that's going to become something else. At this stage, we don't know what that is, and that's going to be the case for all of these sizes. Why? Because basically we're going to fix these collection efficiencies. So if we're fixing the collection efficiencies, then we're going to work out the Stokes number in system A, our model cyclone, and then we're going to work out what that would be in system B to give us the same Stokes number and therefore the same collection efficiencies. That's a bit of a long-winded introduction, but hopefully you've got basically the essence of what we're intending to do. So let's get straight into the actual detail. It's all about Stokes number, and a good starting point would be to actually write down what the Stokes number is. The Stokes number is particle diameter squared. Okay, the density of the solid and the velocity of the gas, the inlet velocity of the gas, and that's all divided by 9 times by the viscosity of the fluid and the diameter, and I've just referred to these diameters as 8-inch and 60 inches. Okay, so that's what the Stokes number is, but we want to preserve the Stokes number. That's what this is all about just here. Stokes A over Stokes B equals unity. That will give us the same Stokes number and therefore the same collection efficiency. So actually the solution that is expected in these two brackets here is basically the Stokes equation, only with the subscripts A for system A and B for system B. It's going to get terribly complicated because I've got rho S and UG, so I'm going to end up dropping these subscripts and use rho A and rho B instead. So let's try and make a little bit more sense out of this. We know that we want Stokes number to be the same. Okay, so if we want Stokes number to be the same, then we are going to have XA squared rho A U A, because they're all on top. And obviously I could put these these collections here underneath, but hold on a minute, we are dividing, so rather than do that, let's make this into ratios, because we want the Stokes number to be the same. So actually, if we do the ratio of particle sizes, that will be XA divided by XB squared rho B U B, and then of course we're dividing by viscosity, so that will become UB and D B over U mu A and D A. Okay, that's great news. Well, don't forget we've got this all equal to unity. So what we can do now is rearrange for XB. So in other words, if we have, and that's Stokes A over Stokes B equals to unity, so that implies that XB equals, if we bring that out over to the left, equals the ratio of the densities, rho A over rho B, UA over UB, that's the ratio of the velocities, ratio of the viscosities, and ratio of the diameters of the cyclone, and obviously that will be XA because we've got that left over here, and we are going to need a square root on this lot just here. So just a quick recap, in just here we have 1 micron and all the other sizes that are in the table just here, 1, 3, 5, 7, 9, 11 and 22. Okay, so that's what we have in system A, 1, 3, 9 and all the other sizes here, and this will be the equivalent size in system B, the industrial cyclone, that has the same collection efficiency as model cyclone over here. That's what I mean by using the Stokes number to predict the performance. This is called a transform. Okay, so let's put some numbers in. The good news about doing ratios like this is we don't have to bother about changing all the units. So long as we've got the same units for density, top and bottom, we don't need it all in SI or any consistent set of units. So what have we got density wise? For the test dust, we had a 2.6 specific gravity and it goes to 1.8. So that is 2.6 goes to 1.8. So that's 2.6 over 1.8. The velocities, on the top we had 18 meters per second. whereas the industrial cyclone, it's 66 feet per second, I believe. Yeah, 66 feet per second. So we do need a conversion there. So that is 66 feet per second, and we need to convert that into meters per second, which I think is 3045. Then we've got the viscosity ratio, which is going to be viscosity of system B, which is 2.2 times 10 to the minus 5 just here, because we're up at a temperature of 120 degrees, whereas the model cyclone was operating at atmospheric conditions of 1.8 times 10 to the minus 5 Pascal seconds. So that's 2.2 over 1.8 times 10 to the minus 5, or we can just simplify that to 22 over 18. So the 10 to the minus 5 will cancel out, and then that leaves us with the diameter, which we decided was 60 inches for system B against 8 inches for system A. Okay, and obviously we need to remember to square root it. Okay, well, let's do some, before we do the square root, let's do some calculations for each one of these. It's easy to go wrong, so I'll do this carefully. I have my trusty, very basic calculator here. So 26 divided by 18 equals 1.44. 1.44. Okay, then we have 18 divided by 66 divided by 0.3045 equals 0.90, near enough, 0.90, 0.90. It's right on the border between being 89 and 90, so there'll be a bit of rounding error, shall we say, on that. 22 divided by 18 is 1.22. 1.22, and 60 divided by 8 is 7.5. I can do that one in my head. Okay, so that's what we need to square root in order to convert values of XA into values of XB, the particle size that gives us the same Stokes number. So we have 1.44 times by 0.9 times by 1.22 times by 7.5 equals 11.86, square root 3.44, slightly over 3.44, so 3.44 and a bit XA. So XB, in situation B, the industrial cyclone, we need 3.5 times more or less bigger dust to give us the same collection efficiency that we were looking at in the model cyclone. So the working out I've just done is basically what goes in here, but clearly there's not enough space. When we come to the transform value, that constant of proportionality, there was a little bit of rounding because in fact the value should be 3.45. So excellent. That means we're at a stage now where we can look at this table, and we have the particle size A, so this is our model cyclone, the 8-inch cyclone, 1 micron particle size, collection efficiency of 20%. Okay, so that's percent. Now we need to transform that, so that 20% of collection efficiency will now in our system B be 3.45 microns, in other words 3.45 times by whatever the value of x was, and we're starting with 1 for the value of x. Now you've got to bear in mind that's going to be a midpoint, because we know what the collection efficiency is at that value. So that is going to be the midpoint of a grade. So here is our grade, or size range, okay, and 3.45 is halfway between 0 and 6.9. What about the next grade? Well, that will obviously start at 6.9 and go on to the twice the value between it and the bottom of the range. So where are we? 3 is going to be split, roughly speaking, that's 3 3s and 9. It's going to be about 10-ish microns, isn't it? Slightly over 10-ish microns. So in other words, if that's the half, and if that was 7, then we'd know that we need to add 3 microns onto the mid side. So that would be 6.9 to 13-ish. Okay, so because whatever you get here, it has to be halfway between these two values. And at this stage, I need to go over to Excel, because otherwise it's going to get painful. So here's the recap of the data. Our original data of particle diameter and collection efficiency. This is the graph that we obtained. So this is Model A system graph. And we then converted that using this transform value 3.45, which is just here. These are the transformed sizes: 3.45, 10.35 in fact, 17.25. You can read the rest of them down here. So this is just multiplying our column B just here by 3.45. And the thing we're keeping fixed is the collection efficiencies. So these collection efficiencies were what we determined from System A, the 8-inch model Cyclone. But it's also the same collection efficiency from the 60-inch industrial Cyclone, but in order to maintain the same Stokes number, we have to use a much bigger particle size to give that collection efficiency. That's what the transform is all about. And then that defines the lower boundary and the upper boundary of the grade of interest, because that is the midpoint in the size range. So that is the lower boundary of the size range, that is the upper boundary of the size range. Okay, so how do we use that? Well, further on in the question, we're given the cumulative mass undersize and the particle diameter plotted against the particle diameter. And you can see there's this fairly faint curve just here that starts at 0 and goes up to 1, or what would be 100%. So let's just consider the upper boundaries, because it's a cumulative mass undersize curve. So at 7 microns, what is the amount of material at 7 microns? It's more or less 0.1, or 10%. That's what's in over here. What about 13.8? Let's call that 14 microns. 14 microns has a value of something in the region of 0.33, which is what we've got here. 20.7 or 21 is just here. 21, we come up to just here. That is round about 0.49. Okay, so the cumulative mass undersize is 0.49, and we carry on doing that with all the other values until, of course, we get to 1. And it's 1 at less than 40 microns. So at these two upper boundary limits, which are both over 40 microns, clearly the mass undersize will be 1 in both cases. Okay, so this gives us the mass fraction in the grades, and I've done what every engineer should do and just check that we haven't made a mistake. We've got that all summing up to 1, because the mass fractions should all sum up to 1. But now this, if you like, is the differential amount in each one of the different grades, where we have our upper boundaries just here, lower boundaries just there. Why do we want the mass fractions? Because, let me just put that to 0 because I want to explain this first. Why do we want that? Why do we want these mass fractions? Because we need to work out the mass of dust being collected. We know the cyclone actually has a feed concentration greater than 0. I'm going to put the real value in a moment or two, but I just want to go over what we're doing here. At 20% collection efficiency, 3.45 is the mid-size of the size grade that we're interested in, the first size grade. We have a mass fraction of the total amount present of 0.1. Okay, that's what we just got from the graph above. So the mass collected, let's put the value back in here. So it's 200 grams per metre cubed is being fed to the industrial cyclone. And therefore, we can do the calculation that the collection efficiency divided by 100, which is what you can see over here. The collection efficiency divided by 100 times by the actual amount that's going in, which is 200 grams per metre cubed, just there, times by the mass fraction of that 200 grams, which is obviously 0.1 for this particular row, gives us 4 grams. So we have 4 grams being collected per every metre cubed of gas that goes through the industrial cyclone. And that's 20.7 grams being collected, and we can come all the way down here. And we know we've got 200 grams going in. What is the total amount being collected? Well, it's the summation of all of these amounts that have been collected per metre cubed. Okay, so we know we've got 120 grams of the 200 grams being collected. So the overall efficiency is 60%. So is a gas cyclone an effective device for removing dust? It's not bad. It obviously works better at higher Stokes number. Higher Stokes number is given by bigger particle sizes, so inevitably it works a lot better at the larger particle sizes. You can clearly see this from this graph here. But it doesn't work terribly well at smaller particle sizes. The gas cyclone has a relatively low pressure drop and can operate at very high temperatures. You don't have to cool the gas stream down before you put it through the gas cyclone. There's no moving parts in the cyclone. So it has those advantages as well. But it's unlikely that you will be permitted in discharging what is near enough 80 grams per metre cube of solids. That actually probably is way too high for a discharge. So it's clearly an initial device for removing solids. You'd probably then have to have a filter after it. The filter would have a much higher pressure drop and may be restricted by the temperature of operation. Okay, so 60% is not a bad efficiency. So that, in terms of the answers, is answer A. The overall efficiency, collection efficiency, is 60%, as we just saw in the spreadsheet. Okay, well, what about pressure drop? Then, what about the pressure drop for the industrial cyclone? The pressure drop is proportional to the, well, sometimes it's called velocity heads, centrifugal heads. Basically, it's the density of the fluid times by the velocity squared. So we can write the equation that delta PB over delta PA is equal to rho. Now this is gas, so I'm going to leave it as just density, because we're going to have to make the assumption the density doesn't change much between room temperature and the temperature, which I think was 200 degrees. I can't remember. We'll make the assumption the density change is relatively small. But we need UB squared over UA. We can square the whole lot or do it inside one bracket. So let's do it inside one bracket. Okay, so clearly our constant, because this was a proportionality, but our constant cancels out because it's on top and bottom, as will the density cancel out. So the pressure drop for our industrial cyclone, delta PB, is going to be equal to 4.5 inches of water gauge. You can convert that to SI by H rho G, height, depth times density, and then we need the ratio of the velocities. Well, the velocity in the industrial cyclone was 66 feet per second, I think. So that's 66 times by 0.3045 divided by the velocity in the model cyclone, which was 18 meters per second. So that's the meters per second values, and we will need to square that. Okay, so let's do that. Let's do that sum. We've got 60 times 0.3045 divided by 18. And we need to square that, so that's 1.015 times by 1.015 times by 4.5, which is not any of those answers, because I get 4.6. I'm sure it should be 5.6 actually. Quick check. 66 meters per second, 66 feet per second, 0.305. 0.305, 66, let's have a quick check. The 66 feet per second, yeah, and we were 305 for the, 0.305. Should be. So delta PB is 4.5 inches times by all that. I'm sure the answer should be 5.6. Shall we have a quick check? 66 times by 0.30. Sometimes this calculator doesn't work terribly well. Divided by 18. Yeah, I must have punched the button because it is 1.1165. So times by 1.1165. That's looking better. 1.25 times by 4.5. 4.5 equals 5.6. My memory was correct this time. So yes, it's 5.6. Now the next question is a really good question. Increasing the temperature of the inlet gas stream will increase or decrease the viscosity. Let's just recap as to why this is an important question. The Stokes number, don't forget, is equal to particle diameter squared, the density of the particles, the gas velocity, divided by 9 times by the viscosity, the gas viscosity, times by the diameter of the cyclone. Let's keep that in mind. So clearly we've got a viscosity here, so would increasing the temperature or decreasing the temperature improve the performance of the gas cyclone? That's the question. Hence the question asks, does the air viscosity increase or decrease as you increase temperature? Now, gas is a fluid just like water. Water, we know the viscosity decreases as you increase the temperature. But hold on a minute, gas is very different from water. Gas has lots of spaces between the molecules, whereas water is a highly compacted system by comparison. 1 mole of water is around about 24 litres as a gas, whereas as a liquid it would only be 18 millilitres, because 1 mole of water has a molecular weight of 18, H2O, molecular weight of 18, so 18 millilitres of water becomes 24 litres as a gas. So there's a lot of gaps between the molecules, and basically what that means is that as you increase the temperature, you will, in fact, of a gas, most gases, you will increase the viscosity. It's the exact opposite of what it is for a liquid. So it's not a good idea to increase the temperature of the gas going into a cyclone with the intention of decreasing the viscosity. It doesn't. It goes the other way. You're actually going to have to chill the gas going into the cyclone if you want to improve the collection efficiency, and that actually takes quite a lot of effort, quite a lot of energy, funnily enough, more energy in decreasing the temperature than there is in increasing it. Okay, so it's not a good idea to increase the temperature. You actually want a lower temperature. Well, by considering the terms in the Stokes number, what else can we do? Well, the obvious one is increase the particle size. If you can increase the particle size, that will have a massive effect on the Stokes number and collection efficiency, because of course it's x squared. Stokes number is proportional to x squared. If we can increase the density, that's difficult, because a material is a material and you can't normally increase the density. You might be able to aggregate the particles going in, but you can't increase the density very easily. What about the inlet velocity? Of course you want that to be as high as possible within the energy or pressure drop that's available to you. What about the viscosity? You really want that to be lowered, and in our case here that means making it colder if possible. If that's easily possible, it's worth doing. If it's going to take an awful energy to do, then it's not worth doing. And then the final one that we want to do is to reduce the diameter of the cyclone, and that comes back to what Dyson did with his cyclones that we use for vacuum cleaners, his bagless cyclones, because instead of 1 or 2 large cyclones, he moved about 10-20 years ago to a series, or parallel rather, collection of much smaller cyclones with a diameter much smaller, and that of course is because D just there is underneath. So the smaller the diameter of the cyclone, the higher the Stokes number, and as per our diagram that we saw just a few moments ago, the higher the Stokes number, the better the collection efficiency will be. So that gave a better performance removing household dust, as indeed it would if you're removing industrial particles from a gas stream. So that's us finished with question 6. Please do look at the part 1 if you want to know more about the theory behind it, but that's been the run through the actual solution to the problem. Thank you.